You are going to be role-playing today. You are in year 8, grade 8, science class. But you're going to be soil scientists. You have been chosen from all of the soil scientists in Oregon because you are the top soil scientists and we need your help. Here in the city of Portland, there's 2 major rivers running through the city and our rivers need you. When it rains, and when it rains heavily here, doesn't it? And all of that pollution on the surface of the road gets washed down into the rivers. And currently it just goes straight down into the rivers. Currently, yes, it was. And as you can imagine, that's not very good for the river. So, you can turn over your worksheet because there are some instructions relevant to this slide. Basically, we have the same information on the slide here that is on the front page of your worksheet. So, you don't need to read it to yourself. We're going to go through this together so we can read it out loud so we don't get lost. So exactly what's on the screen is what is on your sheet. And in a moment, you are going to be getting into groups of 3. It's going to be 3 groups total, actually. Yeah, groups of 2. So you're going to choose your role. And in this panel, your task is going to be to try and solve the problem of the water pollution running straight into the rivers. And there are 3 roles, as you can see. There's a head scientist role, there's a methods and data collector, and there is a technician who's going to actually do the work and do the experiment. So, can I have a volunteer to read out the task? You can either read from your sheet or from the screen, it's the same writing.
Your team of soil scientists have been asked by the City of Portland to create a system that will clean rainwater that runs off roads into drains.
Thank you very much, Wyatt. Who would like to read the problem? Thank you, Sean.
After heavy rainfall events, rainwater washes dust and particles from car exhaust fumes on the road surface into storm drains. This polluted water currently runs directly into the Willamette and Columbia River without being treated. After heavy rains, the water levels in the rivers can rise very quickly, causing a risk of flood.
Thank you very much. Who would like to read the coming up with a solution? Thank you for volunteering, Louisa.
The head scientist in your group suggests that you try to create a rainwater collection bed that mimics natural soil filtration processes.
Very good. You can read the second bullet.
Use your knowledge of soil layers and qualities to test several options that use soil to remove both particles of pollution and chemicals, and to slow the flow of water into the rivers.
All right, so we've got a few things to think about there, but there are some constraints. Who would like to read constraints? David or Dom? David?
Sure. You are under a tight budget constraint. Get off to a very good start.
That's okay.
Therefore, you must find the most efficient combination of soil types. If your design is effective and affordable, it will be rolled out across the city.
Very good. So you are gathered here today to create a model of something that might be implemented in the real world. And in front of you on this desk you can see some different tools that you could create to mimic a real life situation. And as you might have noticed on the first screen, soil is made up of different layers. So you've got the grass at the top, and then this here is a more topsoil, which has organic matter and decaying roots and leaves in it. And then lower down there's usually more sandy soil and the bedrock. So we're not going to be working on the bedrock. We're going to be working with the layers that are the sandy layers and the organic matter layers. And you are going to be creating a model of these layers, and you're going to be doing some tests. So you've got some dirty brown water with particulates in, and I have got another sample that has chemicals in, which I will show you soon. But we're going to do a quick recap, because if you remember, there are some important things about soils that you already know because you're top soil scientists. So does anyone want to describe what this graph is showing me? It's showing everybody. Sean?
It's like a comparison of soil particle size?
Exactly. Which is the biggest one?
Gravel.
Gravel. Very good. So I'm simplifying this, but as you can see, gravel particle size is the biggest, going down to sand, silt, and clay. And as you remember from our lesson yesterday, the pore size in between the particles is going to be smaller. If there's lots and lots of tiny clay particles, there's not going to be much pore space between the clay, so there's going to be not very much room for air and not very much room for storing water. So as your particle size gets a bit bigger, then the sand, say for example between sand particles, do you think there's going to be more room for holding water? Yeah, so there's an interesting thing about that. There's more space to hold air and water, but some of these particles have better properties of actually holding the water in those spaces. So even though you think sand would have more, it does have more room, but have you poured water on sand, anybody? What happens to it? Does it stay on the surface or does it drain in? Drains in, doesn't it? So those pore spaces often are actually quite good for draining water through. Whereas you might remember on our next slide, I'm going to show you about clay. And clay is a really cool particle, or yeah, I guess you could call it a particle, because it has a negative charge and it actually attracts other atoms with positive charges. And they are called cations when they've got a positive charge. So this is a positively charged ion of an atom, and all of these things might be nutrients that are, it's really good to have clay in the soil because it attracts the nutrients, keeps them there for the plants. But a chemical in water might have a positive charge. So you want to think about that. Also, organic matter is negatively charged, and so that can also hold water in the soil. So there's a couple of things for you to think about when you're designing your experiment. And that's just my cue to remind you. What you're going to do is get into your groups of 2 people, and you're going to turn your sheet over. When you get into groups of 2, you can work through the questions. You've got to write down your variables, like whether your variable is dependent or independent. Yes.
You want us to get into 2 groups of 3 or 3 groups of 2?
Good question. I want you to get into pairs. So you'll be in 3 groups. So we're going to write down whether your variables are independent or dependent, and then you're going to come up with a hypothesis. So if everyone's looking at page 2, it's going to help you. Sorry. You're going to come up with your hypotheses. It's going to be 2 different things that we're testing for. We're testing for the chemical removal and for the particulate removal. And if you see, we're going to be using the way of creating a hypothesis that uses the if something, something, then something, something. Do you remember that? So I've started writing out for this lesson to speed things up. So if one of the variables is affected by the other variable, so you're always going to say if it has to be a dependent variable is affected by an independent variable, then something's going to happen. And it's going to be 2 versions of that, one for the particulate and one for the chemical removal. And you're going to be setting up your methods. I showed you a few pictures on this on the second page. If you'd like to turn over, you can see there's 3 pictures. And here's demo. So I put some soil in the bottom. I put some sand in the bottom, because that's the way it is in real life. And I put some topsoil on the top. But you don't have to just do that model, because you want to use as minimal amount of material as possible. So if you can get away with just using sand to get rid of your chemicals and particulate matter, then your model will be more efficient. And this, if the model that you choose, the model that you find that works the best, you'll be able to replicate it in the real world along the roads of Portland. So what we do here, I've demonstrated here, this cup has got holes in the bottom. So each group has got 3 cups with holes in the bottom. And don't forget, when you rest your big cup in your small cup, put a toothpick down the side, because that will let some air escape. So it will help with the process of the water dripping down into the one below. And not everybody has small cups, so you get to use one of these containers. Okay. Does anyone have any questions about the procedure? Yes, Louisa.
What is the cost of topsoil and the cost of sand? So we know which one is more cost effective.
They cost the same. Okay. So, kind of a test of whether you need to use both, or one of one, or one of the other. Does that make sense? That is a really good question. I hadn't actually built that in. So I've done 3 scenarios here, but if you come up with a different scenario, then you're welcome to try a different scenario than the 3 that I wrote out as suggestions. And somebody can use this demo one. So there's a group here. Before you start, there's 2 clear cups for transporting dirty water, one for dirty water, and one, now for the big reveal. Chemicals are going to be represented by crush.
Big crush.
Juice. So hopefully something happens when the chemicals
That's in that big crush.
in this are filtered. All right, so you're gonna collect your grape juice in a cup and your muddy water in a cup. Oh yeah, I just realised what I did. So I said 3 roles, and then I kept on talking about 2 groups. Dominic, you're clever.
Thank you.
You're being very polite. I set it up 3 times. You see the point. You can have an extra person. I think it will be fun to have just the 3 experiments running. Yeah. So you can share the role. The idea with having 3 roles is, as you can imagine, if somebody feels like writing that day, they can write, and if somebody feels like giving instructions, they can read. Okay, but you're adults, so you can do that. So, I mean, you're pretending to be children. Come on up, and actually, let's stand up at the front and get yourself in alphabetical order with your first name. People are close to A, that end. And then the person next to you is going to be your partner.
D. D.
Oh, 2 E's.
L.